Okay, in this video we're going to talk about continuous probability distributions. Previous chapter we talked about discrete probability distributions. Now we're going to talk about continuous probability distributions. And make sure you understand the difference between discrete and continuous. Remember, discrete stands for whole number data types. You can only attain whole numbers. And continuous, you can attain numbers between those whole numbers. So 2.75 as opposed to just the value 2. And in this section here, we're going to talk about uniform and standard normal distributions here. So I'm going to give you some examples of continuous probability distributions. The example that I gave you in the previous chapter was the binomial probability distribution. That was a discrete probability distribution. And now in this section, I'm going to have two examples for you. One is relatively simple, uniform, and the other one's a little bit more involved, standard normal, and the normal distributions. So, proverb for this section: the wicked flee when no one pursues, but the righteous are bold as a lion. In other words, be bold, stand up to your fears, and you'll see there's nothing to fear. I mean, if you're in the right and you're doing what is right, there's nothing to fear. So, let's take a look at this decision tree. I've showed you this beforehand. The very first question that you need to answer when you're looking at probability distributions is whether your data type is discrete or continuous. And so then you'd go down this decision tree to choose one of these. This is not an exhaustive list, by the way, but you'll choose one of these probability distributions. And if it's a discrete data type, then you're going to use one of these. We looked at the example binomial probability distribution. And if it's continuous random variable, then we're going to take a look at all of these. In this section, we're going to take a look at uniform and normal and standard normal. There's a slight difference between the two, between normal and standard normal. Obviously, there's a big difference between uniform and normal. Okay, so let's get to some definitions here. We're going to take a look at uniform, or sometimes called rectangular distribution, because it looks like a rectangle, normal distribution, and standard normal distribution. The only difference between these is that the standard normal has been standardized by using z-scores. We'll take a look at that in more detail a little bit later. So please note that continuous random variables are typically represented by curves, and discrete random variables are typically represented by histograms. Let me give you an example of that in the next slide. So we have a discrete random variable. Binomial distribution is an example of a discrete random variable. It is bell-shaped, but take note that the data types are only whole numbers, not 5.75, not 5.6. Just the value 5 could be attained from the data type. Whereas over here we have a standard normal distribution. It's continuous data. That means all these values can be attained between -1 and 0, or between 1 and 0 and 1, right? These values can be attained, and therefore we have a curve instead of bars that are representing those values. Okay, so what is a density curve? That's another name for a continuous probability distribution. So a density curve is the graph of a continuous probability distribution. What is the graph of the rectangle? Well, it's just a horizontal line. Remember, there's something special about the area underneath. We'll get to that in just a second. But we have a horizontal line, we have a triangle, we have a curve that is a bell-shaped curve, right? A right-tailed or a left-tailed bell curve as well. That's skewed right or skewed left. Now, here's the important part. The total area underneath the curve must equal 1. Why? Why do you think that is? The total area underneath this curve, this curve, this curve, every single one of these blue areas, the area underneath the curve better be 1. Well, that's because we're going to take 100% of the probability. There's no way of getting more than 100%. All of the probability and distribute it. And distribute it according to this curve, or distribute it according to this curve. So the total area underneath the curve, this rectangle has an area of 1. This bell-shaped curve, the area underneath here is 1. Next, every point on the curve must have a vertical height that is 0 or greater. And that also makes sense because every single one of these points, if you will, has a positive probability, 0 or greater. There's no such thing as a negative probability. Remember from the two criteria that a probability distribution has to have the sum of all the probabilities in the column has to be equal to 1, and none of them better be greater than 1 or less than 0. They cannot be negative probabilities. Okay, so important information for continuous probability distributions. I'll ask this on the test. What's the total area underneath the curve? It equals 1, and every point on the curve must have a vertical height that is 0 or greater. Two important points again, because the total area underneath the curve, underneath the density curve, is equal to 1, there is a correspondence between area and probability. And I mentioned that already, that we're taking 100% of the probability and distributing it according to this curve now, because we're dealing with a continuous random variable, right? Number 2, to find the probability in continuous distribution, just find the area underneath the curve. So if you found the area underneath this entire curve, remember, this thing never touches. It keeps going on. This curve never touches the x-axis. This curve never touches the x-axis. It goes infinitely into the left and to the right, and it becomes infinitesimally close to the x-axis, but never touches. Nonetheless, we can mathematically prove with some calculus that the area underneath the curve is equal to exactly 1. And here's a preview of what that looks like. I'll show you guys a little bit later in the next video when we're dealing with the normal and the standard normal curves, how that calculus works, the idea behind it. But hopefully there's a smile on your face here. We are going to allow our calculator to do the calculation to find out what is the area between mu minus sigma and mu minus 2 sigma. What is that area? Well, it's not exactly a triangle, right? It's not exactly a trapezoid here. What is that area? We have to figure that out. And so there's a one-to-one correspondence between area and probability, and in order to find the probability, you need to find the area underneath the curve. So let's get to our first example, uniform distribution, or sometimes called the rectangular distribution. It's the simplest type of continuous probability distribution because it's in the shape of a rectangle. The random variables values are spread evenly over the range because it's uniform, right? It's evenly over the range. Graph results in a rectangular shape. Finding the probability is the same thing as finding the area of a rectangle. That's really simple because base times height is the area of a rectangle. Now, let me give you some examples, some applications of where rectangular distributions would be used, some very basic ones. They're very similar one to the other, using some time. First example, you show up at a bus stop to wait for a bus that comes by once per hour. You do not know what time the bus came last, and so the arrival time of the next bus is a continuous, uniform distribution between 0 and 1 measured in hours. So you know that if the bus just left, then you're going to have to wait an entire hour, right? If I don't know when the bus left last, maybe it left last about 30 minutes ago, then I have only 30 minutes left to wait. But the probability of me waiting an entire hour, or the probability of me waiting an entire 30 minutes, right, is the same. The probability of waiting an hour, probability of waiting 30 minutes, the probability of waiting 27 minutes is the same because I don't know when the bus left next, right? That's unknown. And therefore the probability of it arriving at any point in time is equally likely between 0 and 1 hours. So that's an example. Another one, a similar thing, but with an elevator. You arrive into a building and are about to take an elevator to your floor. Once you call the elevator by pressing the button, it will take between 0 and 40 seconds to arrive. So I'm guessing 40 seconds is when it's at the highest away from you, farthest away from your floor. And then what if it actually ends up on your floor when you press the button? Then it opens automatically, right? So you have to wait between 0 and 40 seconds, and you don't know which floor it's on when you press that button. So the probability of the doors opening is equally likely between 0 and 40 seconds. So we will assume that the elevator arrives uniformly between 0 and 40 seconds after you press the button. In this case, A is 0 and B is 40, the endpoints of your interval And again, in both of these examples, the easiest case was time to use because it's a continuous random variable, and the chances of the bus arriving or the chances of your elevator coming up to your floor are equally likely at any second or any minute in time for either of these examples. Hopefully that gives you a little bit of intuition where uniform distribution is used. It's when the probabilities of all of the occurrences are equally likely. Okay, and so here's our picture of it. Find the probability of class length. So suppose that we have a class. A class length usually goes for 50 minutes, let's say, before we take our break. If it's a face-to-face class, and you found out that an instructor usually goes a little bit over, so he or she can actually finish on time at 50 minutes, or there might be actually 2 minutes that the instructor goes over. You don't know how long he's going to go over or she's going to over, but you do know that the probability of the instructor ending is the same at any one of those points in time. So the class length could be 50 minutes. The class length could be 52 minutes. And so the question could be asked, well, what's the probability that the instructor ends between 51.5 minutes and 52 minutes? And all that is finding out what is the area of this rectangle. What is the probability that the instructor ends the class between 51.5 and 52 minutes? Well, there's that length of time. That's half a minute, right? And then we have the probability, which is 0.5. So 0.5 times 0.5 would be 0.25. So 0.25 is the probability that the instructor will end class between 51.5 minutes and 52 minutes. Okay, you might have some questions that are showing up in your mind. Hopefully, you probably understand what this stands for. That's the class length, right? And you're hopefully understanding that the area underneath the curve, underneath this curve right here, the horizontal line, is the synonymous with the probability. But the question that I'd like to pose for you guys to think about, start thinking about, is where in the world do I get this number right here, 0.5? Why is it not 2? Why is it not 1? Well, to answer that question really quickly is, you know that the height is probability, right? It's a probability distribution, so it can't be greater than 1. That's for sure. It can't be less than 0. And so then you know it has these values has to be between 0 and 1. But why specifically 0.5? Okay, so hopefully you're starting to think about that. And here's where the answer comes. The formal definition for the density function for the uniform distribution is given by this function. It's a horizontal line of b minus a, 1 over b minus a specifically. So y is equal to 1 divided by b minus a for these values between a and b. So if we go to our previous example right here, we had our a and our b be 50 and 52, right? 50 and 52. And when I go through and find out what is the y value, what is the horizontal height, if you will, of my probability distribution, I take 1 divided by b minus a, which is equal to 1 divided by 52 minus 50, and that equals 1/2. So that is how we got 0.5 over here. That is how we got 0.5 right here. We did 1 divided by the length of this right here, the length of my x-axis possibilities. Now let's ask the question, why does it make sense? Why does that formula make sense? Well, remember, if it's going to be a probability distribution, then the area underneath the curve, this entire rectangle, has to equal what? The probability has to equal 1. And so if I have a distance here of 2 units from 50 to 52, that's 2 units, what do you think this height has to be in order for the area to equal 1? Well, if this is 2, 2 times what height would give you an area of 1? Well, 2 times 1/2, right? Let me draw this out instead of using my red little cursor there. So here's 50, and here's 52, right? And the question is, how do I know how to find that? If it's a uniform distribution, it'll be rectangle. and I know what the area is. The area underneath here is equal to 1. That represents all of the probability. And so if I have this distance right here, this distance is 2 because I did 52 minus 50, then what is the height? Well, we have a formula for the area. Area is equal to base times height. And we know that the area is equal to 1. And we found that the base is equal to 2. So what's the height equal to? What is the height equal to? Well, solve this really quick equation, easy equation for the height, and you get that h is equal to 1/2. So in order for this area to be 1, we're given that this this length is 2 units. Therefore, base times height better be 1/2. Base times height better be 1, and therefore the height has to be 1/2. I hope that's a little bit more intuitive as to how to find the height of a uniform distribution. Well, it obviously is directly related to the values that your random variable can take on. What is that interval? Okay, so it's always going to be 1 over b minus a. 1 over b minus a. Let's do some more examples here. Let x be a uniform random variable. Find the density function for each and a graph. So please do practice this. This is incredibly important to actually draw the pictures. When you draw the pictures, you have a better understanding of what you're looking for. And I'll be asking you guys for your work when you guys are submitting that to draw the picture. And that will be worth a point on the quiz or the test, okay? Make sure you draw those pictures, whether it's uniform or whether it's continuous, uniform random variable, which is a continuous random variable, or you have the standard normal probability distribution, which is also continuous. Draw pictures for both. So let's do a couple of examples here. Of full-blown example, if x is between 0 and 5, find what is the probability that x is greater than 4. Okay, so x is greater than 4, and then p is what is the probability of x being between 1 and 5. So if we drew a uniform distribution, here's a uniform distribution from 0 to 5. You can draw a rectangle right away. What should this height equal? Well, if I already know that this is 5 units, then the result would be that this height should be 1 divided by that. That's just the reciprocal of the distance. Again, I can do some math here. A is equal to 1, remember. A is equal to base times height. That's how I find the area of my rectangle. And so if A is equal to 1 and the base is equal to 5, then solving for h, divide by 5, h is equal to 1/5. So this height will always be the reciprocal of whatever the distance is here. Okay? Why? Again, the probability has to equal 1. Okay, so we have some questions. What's the probability? Here's number 1. What's the probability that x is going to be greater than 4? Well, somewhere over here, I'll just redraw each picture over and over again. Here's 0, 5, here's 1/5. Somewhere over here, there's 4. And to find the probability, that just means find the area of this rectangle right here. Well, what's the rectangle width? The rectangle is 5 minus 4, so this is equal to 5 minus 4, just 1, times the height, which is 1/2. Okay, and we have 1 times 1/2. 1 times 1/2 is equal to 50%, or 1/2. The probability is 0.5. Okay, let's do another one. The other one was 2 probability of x being between 1 and 5, if I recall. Yep, 1 and 5. Okay, well, draw a picture again. Here's 0, here's 5, here's 1/5. Between 1 and 5, I find 1 over here and find the area of this rectangle. Again, the area would be equal to 5 minus 1, that's the base, 5 minus 1, and then times the height, which is 1/5. Oh, whoops. I need to go back here. This is a complete mistake. You're probably thinking, what just went on? Okay, on number 1, I was used to having the height being 1/2, and so I wrote down 1/2. Let me fix that really quick. It should be 1/5. 1/5 everywhere. Okay, now you're probably thinking that is more like it. 1/5. So 1/5 is equal to 0.20. There we go. That's the probability. And it is. Think about it. This is 1/5, right? If you say 0, 1, 2, 3, 4, 5, 5 segments, this is 1/5 of the entire rectangle. Okay, that's a little bit more. That's a lot better in terms of correctness. So same thing over here. We have 5 minus 1 times 1/5. Now for the distance between 1 and 5. So we have 4 now times 1/5. 4 times 1/5 is 4/5, or the same thing as 0.80 for the probability. You're welcome to leave your probability as a fraction or a decimal. I'll try to note always for you to leave it your probability usually to 2 decimal places or to 3 decimal places. I'll mention that in the exercises. Okay? So uniform distribution is pretty easy to work with. It's a rectangle. Find the area underneath the rectangle. How do I find the height of the rectangle? Well, it's the reciprocal of the domain, reciprocal of the values that your random variable can take on. So if the random variable can take on 0 to 5, then 5 minus 0 is 5, and the reciprocal of that is 1/5. Why is it the case that the height is the reciprocal? The base times the height better equal to 1, representing 100% of the probability. Okay, let's try some more. There's, if x is between 6 and 12, find the following, A, B, C. So now it's between 6 and 12. I'll draw the picture. Here's the uniform probability between 6, and by the way, you can do this and 12, right? Or you can draw a picture that looks like this. Here's 6, here's 12. The second was probably a little bit more accurate because usually people start with 0 right here, right? Either one's fine as long as you label the horizontal axis. Well, if this is 6 units, then this better be 1/6, because 6 times 1/6 gives me an area of 1. Okay, so we kind of prepared our picture. That's the picture that I was referring to earlier that you need to draw for yourself. So for part A, then, I was using numbers. It was supposed to be letters. For part A, find probability that x is greater than 6. Okay, so probability that x is greater than 6. And if I draw a picture that for that, here is 6, here is 12, here's my rectangle. I know the height of my rectangle is 1/6. So greater than 6 means I take here and all the way to 12. Those are the only values that my probability can attain. What's the area of the entire rectangle? It's equal to 1. Of course, you can do the steps. 12 minus 6 times 1/6, which is 6 times 1/6, or is equal to 1. Okay. Part B, the probability there is less than 5. Okay, so probability that x is less than 5. Well, drawing a picture again, my values that I can attain are between 6 and 12 only. And so here, being the height being 1/6, less than 5, if 5 was right here somewhere, I don't have any probability allocated to be less than 5. Therefore, I have, think about this, no probability means the height of my rectangle would be 0, right? I could say that there is a horizontal distance. Sure, the horizontal distance is 6 minus 5, which is equal to 1. But I don't have a vertical distance because there's no probability that's been allocated for that interval. So 1 times 0 obviously is 0. Okay? And similar thing for probability that x is greater than 12. Think about that. So for part C, probability that x is greater than 12, the picture would look like this. Here's 6, here's 12, here's my rectangular distribution, 1/6. So greater than 12 means to the right of 12. And since there's no probability that's been allocated to the right of 12, again, everything to the right of 12, you can think about this as an infinite interval. But if we have whatever the large number is, times 0, the probability would be 0 as well. There's no probability that's been allocated to the right of 12. Okay? I hope that makes a little bit more sense in terms of uniform probability distributions. Let's do some more examples really quick. It says an electricity provider says that any voltage amount between 123 and 125 volts is possible, and all of the possible values are equally likely. Therefore, there's 2 units between these two, and therefore the height of my rectangle should be 0.5. Right? 2 times 0.5 is going to be 1. And then the question is, find the probability that a randomly selected voltage level is greater than 124.3. So we need to find 124.3 somewhere here, right? Find the difference, and then find the area of the rectangle. So let's do that really quickly over here. So we have a picture that looks like this, 123, and the other one was 125. And we're looking for 124.3 or greater, right? So this was 1/2. 124.3 or greater means I'm going to be looking for that probability, that area. So probability that x is greater than 124.3 is equal to, well, 125 minus 124.3 times the height, which is 1/2. And 125 minus 124.3 is 0.7. So 0.7 times 0.5, if you change that half to decimal form, 7 times 5 is 35, and move the decimal place twice. That means that you have a probability of 0.35. Okay? That's how you go about finding the probability in this case. And last one for the uniform distribution example and for this video until we go on to continuous random variable for the standard normal. Your friend has a pattern of coming late to all of their meetings. You know that their tardiness is distributed uniformly and continuously, right? You don't know when they're going to come, and there's probability of them coming at any point in time is equally likely. Let x be the number of minutes they are late. Suppose they are late between 0 and 30 minutes. And so we have these steps here, 4 steps. Draw a uniform distribution graph for this example. So 0 to 30 is our horizontal. So 0 to 30. Do we already know what the height is? Yes, if this is 30, then this has to be 1/30th, because 1/30th times 30 is equal to 1. So that's number 1. That is the probability distribution. The area underneath that curve in the box, in the rectangle, is equal to 1. Number 2, what is the probability that your friend will be late less than 10 minutes? Less than 10 minutes. So if I draw probability that your friend is late less than 10 minutes, the picture to go along with that would be 0 to 30. Here's 1/30th, and here's 10. So less than 10 minutes would be this side of my rectangle. So the probability then would be 10 minus 0 times the height, which is 1/30th, or 10 times 1/30th, 10 times 1/30th, which is 10/30ths, or 1/3, or approximately 0.33 rounded to 2 decimal places. So there's 33% chance that your friend will be late less than 10 minutes. Okay. Number 3, what is the probability that your friend will be between 20 and 25 minutes late? Well, we can do that as well. Number 3, probability that your friend is late between 20 and 25 minutes. The picture to go along with that would be 0 again to 30. The height is 1/30th. And I'm looking for this interval, 20 to 25, somewhere in here. 20 to 25. So finding the area underneath the curve on that interval gives me the probability that your friend's going to be late between 20 and 25 minutes. So we can find that out by saying 25 minus 20, which is obviously 5, times 1/30th. So 5 times 1/30th is the same thing as 5/30ths. right? And we can either simplify that or just divide 5 divided by 30 to get our decimal form, and that would be 0.16666 repeating. I'll put 0.167 and say that's an approximation. So about 16-17% chance that they will be late between 20 and 25 minutes. And there was one more. Find the probability that they're going to be late more than 20 minutes. So we can do that. Again, drawing a picture. Probability that they're going to be late more than 20 minutes. We have 0 to 30 minutes that they can be late. They're not late more than 30 minutes. And they're equally likely to be late all of the minutes between 0 and 30. So we have 1/30th for the height. And we're looking for greater than 20. So 20 is some over here. And greater than 20 would be all of that area, which means I can find out by 30 minus 20, and then multiplying by the height, 1/30th. So 10 times 1/30th, which is 10/30ths, or 1/3, which is approximately 0.33 or 33% chance that your friend will be late between 20 and 30 minutes late. I hope that you guys have some intuition now with rectangular or uniform distribution, what it looks like. It's a rectangle, and how to set it up, set up the picture, and how to find the probabilities. It's really easy. You don't even need a calculator to calculate these probabilities. You will need a calculator for the next probability distribution that we're going to talk about in the next video, which is the normal and the standard normal distributions. So get your calculator out if you don't have it, your graphing calculator.